Alright, tech enthusiasts, let's kick things off with Neural Architecture Search, or NAS. Think of it like this. You're building a skyscraper, but instead of designing each floor manually, which takes forever and could totally miss out on innovative approaches, NAS uses AI to automatically design the optimal architecture. It explores thousands of potential designs, searching for the best combination of layers, operations, and hyperparameters. This results in far more efficient networks, specifically designed for a particular task with dramatically reduced latency and resource usage. Imagine a model doing ImageNet classification, but using a fraction of the processing power. That's the power of NAS. We saw some incredible examples of this in the articles, like NVIDIA's Llama 3.1, Nematron 51B, running 4x larger workloads on a single GPU. A massive leap in efficiency thanks to NAS. And in the context of efficient implementation for particle physics experiments at the LHC, we saw how NAS coupled with pruning and quantization-aware training, QAT, yielded over 25 times reduction in computational cost for jet classification, a truly remarkable achievement. Another interesting application is in the deep spiking neural networks, where NAS is used to find optimal architectures involving recurrent motifs or sparse connections for large networks. That's not just faster. It's game-changing for energy efficiency. We're talking about pushing the boundaries of what AI can do on resource-constrained devices. Picture the possibilities: faster, more powerful AI, not just in your data center or the cloud, but at the edge, allowing for real-time processing on mobile devices and more. The future of AI is efficient AI, and NAS is showing us the way. Now, let's talk about AutoML, or automated machine learning. This is where things get really exciting because it's making AI accessible to everyone, not just data scientists. AutoML automates the entire machine learning process, from data preparation and feature engineering to model selection, hyperparameter tuning, and evaluation. Previously, building accurate and efficient ML models required years of training and expertise. Now, it's way more accessible, using things like Google Cloud AutoML or similar tools. But what does that actually mean in terms of impact? Imagine a medical researcher who wants to automate cancer cell detection. Instead of writing countless lines of code and meticulously tuning hyperparameters, they can use AutoML to build a highly accurate model relatively quickly, opening the way for faster breakthroughs in diagnostics. Think about a company attempting to improve fraud detection by analyzing transaction data for anomaly detection. They can efficiently create and train a robust model much more quickly and, crucially, with little need for advanced data science skills. And we've seen some other impressive examples from the reviewed articles. For example, GenomeNet Architect. That's an amazing AutoML framework designed to optimize deep learning models for genomic data analysis. And it has demonstrated top performance on virus classification and pathogenicity tasks, showcasing the power of AutoML in solving complex biological problems. Another impressive example of AutoML is in the use of pre-trained transformer models, enhancing AutoML systems that can handle multimodal data efficiently, E.G, tabular, text, image data, such as that used in object detection or image captioning for text vision. We also observed its potential to improve the reliability and speed of business process automation in the articles covering various AutoML tools. We're talking about streamlining workflows, reducing time and costs, while improving overall model accuracy and results. AutoML is not just automating a task, it's transforming industries by democratizing the power of machine learning. Next up, the talk of the town: LLMs, or large language models. These AI powerhouses are absolutely revolutionizing the way we interact with computers. You've probably heard of ChatGPT, Bard, or similar tools. They're all examples of LLMs. These models understand and generate human language, completing tasks such as translation, text summarization, question answering, and much more. They're not just for chatbots. They're a force of nature capable of transforming numerous tasks in multiple areas. But their impact and capabilities go far beyond casual conversations. In this review, we've seen some truly revolutionary applications. For example, using LLMs as a tool to discover and search for patterns in code, through tools like FunSearch, to generate new mathematical constructions and build higher-performing computer programs. Now, imagine an engineer using FunSearch to create algorithms that would solve really hard problems. This system searches for effective algorithms. With input specifications and program templates available to the tool, new solutions are readily discovered, thereby extending human understanding and capabilities. And in the context of optimizing existing large language models, we observed how NVIDIA leverages LLMs, in essence, fine-tuning and other modifications, to create extremely efficient implementations for use on a single GPU, outperforming many of its peers in speed and accuracy. And in the context of developing deep learning models for medical applications, we found out how LLMs can aid in building robust and explainable models for diagnosing complicated disease states, like that of autonomic dysreflexia, by optimizing the selection of critical features using methods such as that of sequential forward selection or recursive feature elimination. The versatility of LLMs is mind-blowing. They're assisting in automating numerous tasks that previously required a lot of human intervention, enhancing efficiency and improving process across the workforce. In essence, LLMs are opening up the world for humans to develop new algorithms, generate applications and code, and create new concepts, making them an indispensable tool in the 2025 technological landscape. Let's shift gears and explore some of the incredible advancements in deep learning. One emerging area is spiking neural networks, or SNNs, which are inspired by the way neurons actually work in the human brain. Unlike traditional neural networks that use continuous values, SNNs transmit information through binary spikes. This event-driven method makes them very energy efficient, leading them to have enormous benefits when incorporated into highly efficient, low-power hardware, especially in edge devices for real-time applications. Additionally, we saw how the rich temporal dynamics inherent in SNNs have helped them outperform conventional methods in tasks involving sequential data, like that used in speech recognition, video processing, and medical diagnostics. One key innovation we analyzed was the development of direct learning algorithms for SNNs, particularly those using surrogate gradient methods. These algorithms bypass some of the challenges associated with the non-differentiable nature of the spike signal, thus making it possible to train large-scale SNN models with impressive accuracy. And in a specific application of SNNs, we investigated examples of how they are used with neuromorphic cameras, thereby gaining incredible improvements in motion estimation and object tracking, showing great potential for low-latency and high-efficiency implementation in real-time applications, such as that of autonomous driving or in-car driver monitoring. We also discussed other important advancements in deep learning architectures, such as the hybrid LSTM transformer models used for real-time multitask predictions in complex engineering systems, as well as advanced methods for optimizing and stabilizing models, such as the use of intrinsic plasticity and recurrent spiking neural networks, which mitigates risks of model instability during model architecture tuning. These innovations are not simply incremental improvements, but represent a potential shift and a new vision for building adaptive and efficient models, using techniques like knowledge distillation. We're looking at models operating not just faster, but also more efficiently on limited resources for a large capacity of targets and tasks. This is making high-performance AI a realistic possibility for numerous applications, such as that of edge computing in sectors like healthcare, manufacturing, and others. Let's transition to the realm of hardware, where we have exciting advancements in energy-efficient AI hardware designed to harness the full potential of these advanced AI models. We reviewed some incredible examples of how scientists and engineers are developing specialized hardware for deep learning, ranging from super-efficient memristor-based artificial neural networks to custom-designed ASICs for tabular data processing. Think about the power of these tiny classifier circuits. They're generating accurate combinational logic for machine learning tasks while using a fraction of the power compared to traditional methods. The cost-effectiveness is staggering, making AI deployment a possibility without the need for energy-intensive hardware such as that of traditional GPU acceleration. In the context of the memristor-based ANNs, we went through the complete circuitry needed for a full hardware implementation including DACs, TIAs, ADCs, and related components. Each design choice, e.g., the use of passive versus active crossbar, presents a trade-off between integration density, power consumption, and accuracy, and using advanced signal processing techniques can greatly mitigate the impact of hardware non-idealities. We discussed and illustrated the different learning algorithms used to train memristor ANN, including both ex situ and in situ methods, and reviewed the different schemes used for programming memristors, highlighting the benefits and limitations of the write verify versus write without verify methods. These are just samples of the rapid developments in the field of efficient hardware deployment and low-cost implementations of AI, specifically targeted applications. We saw some really exciting and sophisticated innovations in the area of hyperscale NAS architectures to power GPU computing for large-scale AI workloads like that of generative AI training. The combination of low-power, efficient AI models such as SNNs combined with innovative hardware options will enable AI to have a transformational impact on numerous sectors, beyond the ones we have discussed. From enhancing business process management using flexible low-code platforms, supporting digital transformation, improving healthcare through enhanced disease detection and more personalized treatment, speeding up drug discovery by using techniques like topological regression to design more robust and accurate QSAR models. improving operations such as that of smart homes by preventing and identifying cyber threats efficiently, and to even enhancing the potential of precision agriculture. The impact of this combined approach will improve across many industries and tasks. As we wrap up this deep dive into the world of AI, let's take a look at the thrilling possibilities and challenges that lie ahead. We've already seen how NAS, AutoML, and LLMs are transforming the AI landscape, resulting in faster model development, greater accessibility, and much higher efficiency. But what does the next few years hold? Several exciting developments could fundamentally reshape the field of artificial intelligence in the coming decade. The increased integration of AI into many fields, such as that of the Internet of Things, promises to unlock several exciting possibilities. There is a potential for even better, more agile, and more comprehensive AI systems. This is already being supported by advancements in edge computing, which has potential both for speeding up processing and improving energy efficiency. In healthcare, the development of more robust and explainable AI models could lead to earlier and improved disease detection, better patient care, and a new generation of personalized medicine. Imagine AI systems that can accurately predict individual disease outcomes based on advanced models of genetics, lifestyle traits, and individual biology, along with high-performance AI algorithms and efficient hardware such as that of SNNs, leading to low-power sensors capable of continuous monitoring. This could be the very definition of precision health. In finance, the enhanced use of AI could increase accuracy and speed in fraud detection, improve risk models, and dramatically improve efficiency. Imagine AI agents capable of managing and executing incredibly complex analysis from financial data combined with an accurate assessment of human dynamics. This approach has the potential to detect financial crimes more quickly and efficiently, helping governments and institutions to monitor compliance and protect consumers. We also explored some of the ongoing innovations in other fields, including genomic prediction models for agriculture and high-efficiency AI algorithms for improving operations, such as that of automated systems. Nevertheless, this revolutionary potential is not without caveats. Ethical considerations and AI safety are paramount. As AI becomes more integrated into our lives, the need for a transparent and rigorous approach becomes even more crucial. Considering the potential impacts of misjudgments in critical applications like medical diagnosis, it is necessary to build a system of controls to minimize risks and to ensure the accountability of all AI efforts and their outcomes. Further, the ever-increasing computational demands of AI imply a need for ongoing development and innovations in computing hardware. We've observed that innovative architectures, such as that of SNNs, and specialized hardware targeted towards specific applications, like that of memristors, show promise in minimizing power consumption and enhancing efficiency. Still, future breakthroughs will be essential to fully realize AI's potential. It's an exciting and responsible race to improve the capabilities of AI systems, creating tools that benefit everyone and safeguard the future.